So in this video, the intention was to kind of cover over all the topics and kind of just recap everything we need to know. Um, but I want to make sure I make special mention of this. As I said in the last video, the 7.5 video, which I've taken down now, I made a really, really, really big error on this one when we were estimating. Sorry, not that one. Made another error there when we're estimating this one. So average we did good, proportion we did good. This one I made a very big boo-boo on in that video. So I'm going to be covering this one in a little bit more detail than the other two. But I am going to kind of recap everything just for a little bit for the average and proportion, just to make sure that we got that down. And then I'll very detailed wise go over what I did wrong here and how to do it correctly, because it's somewhat of a small error, but it's something that if I can make it, obviously anybody can make it. Not to toot my own horn there. So what we're going to focus on first is kind of how to decipher when to use which method. So remember, proportion deals with when you're estimating a percentage. Mean deals with estimating an average, and that's either the mean with the standard deviation known, which is a z-score, or if the population deviation is unknown, which is a t-score. This is going to kind of be the main idea of how to know when to use the z and when to use the t, because this is the one where people will often get confused on and mess up which score to use. So real quick here, let's go over some questions you can kind of ask yourself or look over and kind of help you figure out which one to use. So if you're going to use a proportion, which is that p hat stuff, so remember proportion is p and p hat and q hat and all that good stuff there. It's a z-score test. Um, these problems usually ask you to estimate a percentage. So what percent of people are this? What percent of people have this? What percent of people do this? So if that's the case, you're doing a z-test for a proportion. You need your p hat, your q hat, your p, and that margin of error formula. If you're asked about an average, it's usually the number of something. So I'll ask you to kind of estimate the number of people that have this, or the number of cats, or the number of dogs, or the number of visits, or the number of car crashes. So if you hear the words estimate the number of, that usually means you're doing an average question. So this could either be a z or a t, depending on whether you know the population or sample deviation. So population deviation is usually given with sigma. Sample deviation is usually given with s, little s. Um, but if you know the population deviation, so if they say that the deviation of car crashes for everybody is 2.5, 2.5 car crashes, then you're going to be doing a z-test because you know the population deviation, you know the deviation that applies to everybody in the population. Whereas if they say, well, from this sample of 100 cases, we got that the deviation was about 2.4, 2.5 car crashes per person. Well, if it's just from the sample, if the deviation just applies to the sample, then that's a t-test because you don't have as much information and you have to account for that greater variability and use a t-test, which are a little bit more forgiving there. And then for variance and deviation questions, they'll usually just ask you to estimate the deviation of or the variance of or something like that. Again, if you saw the error-prone video, then you kind of know a little bit about what to do here. If you didn't, then again, we'll cover this one in a second. So let's tackle the average one first here. So it says we have an outbreak that spreads to a population of 100,000 people. And it says that out of 100 infected people, the average age is 75 with a deviation of 3. What's the best estimate for the average? So estimate for the average. So I know I'm going to be using either a z or a t, and I'm going to be testing the average. Usually the average we call a mu. So if we're testing the average, this is the variable that we use, the mu symbol. Now we have to figure out, okay, is this a t or a z? Well, it says out of 100 people infected, the average age is 75 with a deviation of 3. So that means that the deviation here applies to just the sample of 100. So this deviation doesn't apply to everybody. It just applies to the 100. It doesn't apply to the 10,000. So in this case, I'm going to be using a t-score test because I only have the deviation for the 100 people, not for everybody in the population. So my margin of error, and again, all these boil down to point estimator plus or minus margin of error. And for an average, your point estimator is simply the average of your sample. So in this case, in this case, 75. So my x bar, my sample average is 75. That's my point estimator. It's going to be 75 plus or minus something. How do I get the plus or minus something? Well, that's when we use the margin of error formula for a t-score. So that's t times the sample over root n. So how do we get this t-score value here? Well, you need two things. You need your alpha and you need your degrees of freedom. So degrees of freedom is just n minus 1, which in this case, out of 100 people, that's going to be 99. Now, if you don't have 99 on your table, you just have to kind of use 100 or close to it as you can get, just because that's as close as you can get. So usually, if you don't have the exact degrees of freedom, you get the closest you can. My alpha in this case is 0.05 because that's the opposite of my confidence interval, essentially. 95% confident means 5% not confident, essentially. So let's go ahead into a t-table here. 99 I don't have, unfortunately, so I'm going to have to stick with the 100 there. So here's my 100 row. And then let's see here, 0.05 and 2 tails, so right there. Go there, go there. I get 1.984. So that is my t-score. So my t is 1.984. Double check that again. Right. So now I can just multiply it to the other fraction here. So this is that thing here. S, remember, is the sample deviation. So that's that 3 there, because that's the deviation of those 100 people over root 100. So you multiply it out. 1.984 times 3 over root 100. And we get 0.595. So we have our average is 75 years plus or minus 0.595. So again, this infection here seems to favor everybody that's around 75 years of age because we have a pretty low margin of error, even for a 95% confidence interval. So it's an infection that pretty consistently targets the same average age there, around 75. Now, what would change here then, this last question down here, it says, what if instead of the sample, what if that 3 represent the population deviation, which means that out of these 10,000 people, we assume that the deviation is 3 rather than just out of these 100. So if this 3 applied to everybody. And usually the way that's phrased is that they'll say, well, from past data or past experience, we know that the deviation of this is typically 3 or 2 or whatever. So that way that's phrased is usually accompanied by the fact that you're looking at past data to help you get that deviation. But if this 3 was applied to the 10,000, not just 100, but this was out of the 10,000, then we'd still do much the same thing. Our x bar would still be 75. But our margin of error would be z times sigma over root n. Well, what's sigma? Well, sigma is just, again, this population deviation now. It's 3. So sigma is basically the S for the entire population, which, again, we're just kind of saying is 3. Now, for a z-score, we know that if my alpha, or rather, for a z-score, we know that if we're doing a 95% confidence level, that's one of those common numbers there. That's 1.96. Again, that's just kind of a common memorized number for a z-table. And then we have our sigma over root 100. And then we get our margin of error here. So 1.96 times 3 over 10, because that's what square root of 100 is. And we get 0.588. 0.588. So 75 years plus or minus 0.588. And you notice how this is a little bit of a tighter estimate? And that's because if you have the population deviation, if you have the deviation of the entire population, then you can afford to be a little bit more narrow in your guessing and a little bit more precise, because you know more information about the population. You know its deviation at least. Whereas here, we didn't know any information about the population at all. We didn't know what the deviation was. So we had to use a little bit more of a broader guess there, which not by much, but a little bit more of a margin of error there to make sure that we were staying within that 95% confident range. So usually your t-score errors are a little bit bigger than your z-score errors of the same alpha or the same confidence level, just because they have to account for the fact that you know a little bit less with a t-score because you're using the sample statistics, not the population data. So it says here that an outbreak occurs of 20,000 people. It's found that after testing 150 of them, 5 are infected. Based on the information, what's the best estimate for the percent of people? So percent means proportion. So we're going to be testing P, which is a z-score test. And remember, for the point estimator for a proportion, that's simply our sample average. So we have 5 out of 150 Let me try that again. P hat is 5 out of 150. And then Q hat is just the reverse of that, but I'll write out here. So 145 out of 150, and then my N is 150. So let's get these percentages here, usually as decimals. So 5 out of 150 is 0.033, 0.033, and then 1 minus that is 0.967. And so then our margin of error for a proportion is my z-score times the square root of p hat, q hat over n. So my z-score, remember, if it's a 95%, we know it's that common number of 1.96. So let's go ahead and type this in here. 1.96 times the square root of 0.033 times 0.967 over 150. And we get 0.028. So 0.02. We'll round that 8 up to a 9 because after the 8's a 5. So 0.029. 0.029, right? Second guess myself every time now. So my interval would be my p hat, so 0.033 plus or minus my margin of error, 0.029. Or if you want to put it as percent, it'd be about 3.3% plus or minus 2.9%. So pretty much 3% plus or minus 3%, essentially. Which is a pretty low percentage, but that's in line with what our population, our sample percentage was. Our sample percentage was a pretty low percentage, 5 out of 150. That's not a lot of people. So it makes sense that our interval is also quite small. Now, this is the one where I'm going to take some time on because this is the one where I messed up on the last video. So we have 30,000 people total. After studying 120 people infected, it's found that the average length of time is 5 days. And it has a deviation of 1.5 days. So kind of think of, again, the deviation is how far away stuff is from the average. So a high deviation means that your data is really spread out. It's really varied. There's not a lot of consistency. So if you're talking about the length of infection, if you have a very high deviation, that means people are infected for a lot of different amount of time. So some people might be infected a really short amount of time. Some people might be infected for a really long amount of time. Whereas if you have a very small deviation, in this case, that means when people get infected, it's usually about the same length of time. So usually people are about the average length of time for the infection. So again, that's what deviation kind of gauges, is how inconsistent or how consistent is your data. So in this case, we have a deviation of 1.5 days, which for an infection, I guess seems kind of small depending on how severe the infection is. What's the best estimate for the deviation of the length of time after the treatment is prescribed using a 95% confidence interval? So this is the data after a treatment has been prescribed. So we're testing a deviation, and the deviation symbol is sigma. That's what we're trying to estimate here. And for a deviation, we actually don't use a z or a t. We use something called a chi-squared test, which is this symbol right here. This is not an x. It's called a chi. It's a Greek letter, kind of a fancy x with a little curl on one of the ends there. And this is not a squared value. This is where I messed up in the last video. This is not a square number. And I knew it. I just overlooked it because I was going too fast or I wasn't focused or I don't know what. But this is a single value you get from tail. This is analogous to a z or a t-score. You do not actually square this number. Right? This does not mean take a number and square it. This is just the variable itself. This entire thing is one variable. Right? It's no different than saying y or z or b or whatever. So the way you get the margin of error for a deviation is unfortunately chi-squareds, unlike z or t, they're not symmetric. So a chi-squared chart might look something like this. So it's not very symmetric, whereas z or t, they're usually a nice bell curve. So if you get this value, you can just copy it over to get its counterpart over here. So this is 1.5, this would be negative 1.5 if those were your critical values. Well, for a chi-squared, if I get this value, because it's not symmetric, it's not necessarily going to be the same as this one over here. So because of that, we actually have to find each one individually, essentially. So the way you get your bounds is you do the following formula. You do the square root of n minus 1, kind of reminds you of degrees of freedom, right? Times s, which is your sample deviation, like for us that'd be 1.5, all over the chi-square here, and we'll call this the chi-squared r. And then over here you have almost the same formula. Sorry, there's a square there too. S squared times s squared. Put those in parentheses too, just to be nice about it. So n minus 1 times s squared over chi squared L. So you actually have two different values you're going to look up in your chi-squared table. And yes, there is a table that goes with this. One for the right and one for the left. Now, you might be thinking, well, this is left and this is right, so why are you putting R and L there? Again, R and L refers to kind of how it would appear in a graph. Basically, think of this one as the larger table value and this one as the smaller table value, because you want this number to be the bigger number because it's on the end of your interval. This is the big N, this is the small n. So this should be the bigger number because you're dividing by a bigger number, which makes the number smaller. And this should be the smaller chi-squared number. That way you're dividing by a smaller number, so the number keeps staying bigger. So how do you get these values? Well, first, you do look it up in the table, but you do have some pre-work here. If you're going to look up a chi-squared number, what you need to first find out is your degrees of freedom, just like you did for a t-table. So that's still n minus 1. So for us, out of 120 people, n minus 1 would be 119. And then you also have to know your alpha, although you're going to do some stuff with it first. So my alpha in this case is 0.05, 95% confidence. But I'm going to split that in half. And why am I splitting in half? Well, if I'm going to find the two numbers individually, I have to manually split in half, one for one end, one for the other end. I didn't have to do this with the T or a Z because the T or a Z are symmetric, so they kind of already pre-did that in the table. But since chi-squareds aren't symmetric, you have to do it yourself. So if you split in half, you get 0.025 here. Here you also get 0.025, but remember, I want the other end here. So what I'm going to do is I'm going to do 1 minus 0.025 and get 0.975. Now, again, the reason I'm doing 1 minus is because if I go to this graph up here, let's say that the way that the tables work, remember, the tables that you're looking at, they're giving you areas and representing them as probabilities, essentially. They're representing it as a rating system. So that means, like, let's say this is my critical value here. This is my chi r. That means that over here is 0.025. That's 0.025 of the area of this curve here, which accounts for the probability. Well, my other one over here, my counterpart, chi-squared L, I basically want 0.025 area there. I want the low end area. Unfortunately, my table doesn't go left and right. My table only gives me one direction. And for chi-squared, that one direction is to the right. So my table will show me this value directly. But if I want this value, I have to think about, okay, if I want this area, that's going to be 1 minus the area to the right of it. Well, if it's 0.025 here, that means to the right of it is going to be 0.975. So I want to look that up in the table because the table is going to give me the area to the right of this number, not the area to the left. So this number is okay. I look that up. I get the area to the right is 0.025. Good to go. This one I had to actually do some manipulation with and figure out, okay, if I want the area to the right, that's 1 minus whatever this value is, which again is 0.025, and that's the value I'm going to look up in the table. So let me show you what a chi-square table looks like. The one in your book's a little bit different, but it's still much the same. It's this little chart here. Let me zoom in a little bit. So up here, you have your alphas essentially, or your probabilities that we just figured out. So here you see 0.025 for this column and 0.975 for this column. So if I was doing a 10% test, I would take 0.1 split in half, and I would get 0.05, and then I would get 0.995. Right? No, sorry. I would get 0.95. So you can kind of see how they kind of go in counterparts here. So 0.025 is 3 spaces in from the right. 0.975 is 3 spaces in from the left. So the tables try to make the table a little bit nice to read in terms of how they position their numbers there. Um, so you can see here clearly we don't have 120 on our degrees of freedom, or 119 here. So we use the closest we can, which is 100. So if we don't have 120, we use the one that's closest. In our case, like I said, that ends up being 100. So I have my alphas up here that I got, 0.025 and 0.975. I'm going to look down them and get my two critical values. So 0.975 is 74.222. Let me write that down here. So 74.222. And then for the other one, it's 129.56. So 129.56. Let me make sure I just double check that. Right. Right. Okay. So those are my two critical values for my chi-squared. So I can go ahead and plug them into this formula here because I have everything I need. I have my n, which is 120. I have my s, which is my 1.5 because it's my sample deviation. And now I have my two critical values. And again, the larger one's going to go over here. The smaller one's going to go over here. That's why we kind of call them right and left, because on the table, bigger one's over here on the right, smaller one will be over here on the left. If you notice, for each row, the smaller numbers are on the left-hand side of the table, and the bigger numbers are on the right-hand side of the table. So that's why they call it R and L, because it's how you look at the table. So n minus 1, we just figured out that's 119. That's what n minus 1 is. So 119 times 1.5 squared over, this is where I messed up on the last video. Like right here, the larger chi-squared would be 129.56. I would not square this number. Chi-squared is the variable, it's not an operation. So I would leave it like that. And then, again, obviously do it in the calculator, but I would not square this bottom number. The variable is called chi-squared. It doesn't mean that you actually square the number itself, which is the mistake I made in the video, and I failed to catch myself on. So 119 over 1 or times 1.5 squared, all over my lower one was 74.222. So now I can go ahead and do this in my calculator. Whoa, there we go. So square root, clear. Square root of 119 times 1.5 squared. Actually, I should probably do it like this. I'm really stickler about my parentheses here. So 119 times 1.5 squared divided by 129.56, and make sure it square roots all of that. 1.44, 1.44 less than sigma less than, and then if we do this again, but with the other one, so 74.222, 1.9 essentially. So we can estimate the population deviation for the length of infection is somewhere between 1.4 and 1.9 days, based on the data that we have here. So when a person gets infected, we can say that the average length of time that they're going to be infected is 5 days, with a deviation of 1.9 at the most, which is, again, a pretty small amount of give for our deviation there, which means our data is pretty much consistent. Again, 2 days for an infection might seem long, but again, just depends on how you view it. If it's like a really bad infection that you're going to die really recently, unless you get care, then that could seem like a very big number. But if it's more of like a mild infection, like maybe the sniffles or cold or something like that, then that 1.9 doesn't seem that big of a deal. So again, it's all a matter of what the perspective is here. But again, my main error on the last video, and again, I apologize for it, is that I squared the number down here when I shouldn't have. This number does not need to be squared. That's just the variable itself. And again, the way you get this variable is you have to take your alpha value, split it in half. Half it goes there. Half it gets the opposite treatment, so 1 minus it. And then you look up these two values in your chi-squared table using your degrees of freedom as the guide for what row to use. And remember, bigger number goes on the bottom of the left fraction, smaller number goes on the bottom of the right fraction. So your small number should be on the left, your bigger number should be on the right when you get done with it. So last one here, just to make sure we get this one down. We have studying the virus in the past. A country collects the results from its hospitals and finds out that for every 300 people tested, an average of 13 of them were found to have the virus. Using the past as a guide, they assume that the population deviation is 1.5. Um, using a 95% interval, estimate the average of number of people that have the virus. So again, estimate the average number of people, average number of people. So if I want the average, that means I'm going to be estimating a mu. So I'm going to be using either z or t and decide which one is it. Well, it says assume the population deviation is 1.5 because they're using a past as a guide. So they caught this virus in the past that's very similar. They said, well, based on that result, we found the deviation was 1.5 in terms of number of people infected. So that means that we have a population deviation, or at least a decent estimate for it. So we're going to be using a z-test because we have the population deviation. We don't need to have this greater variability. We can use that as our guide. So that means that I have my point estimate, which is the average, so 13, and I have my sigma, which is 1.5. And so I need my z-score, which for 95%, again, that's a common number, 1.96. So then I can make my margin of error. So it's my z-score times my sigma over root n, which is 300 because I had 300 people tested, right? 300 people. So 1.96 times 1.5 over square root 300. And we get 0.1697. So we'll just round off to 0.17. So 0.17, making sure I double check my work again. Yeah, that looks good. So my margin of error is that, so that means that my average is 13 plus or minus 0.17. Again, we're not doing a proportion, so there's no dividing needed. Some people might take 13 divided by 300 because that's what you would do if they asked you for the percent of people infected. So it's a very, again, averages and proportions can get kind of mixed up too because you can talk about them in kind of the same, like if I said how many people are infected, you can give me the percent of people infected or you can give me the actual average number of people infected. And those are both kind of describing the same thing. So once again, read the question, take some time and think about what one makes the most sense in each case. Are they asking for a percentage or are they asking for an average? If they're asking for a percentage, by all means, find the percentage. But if they're asking for an average, you don't need to worry about it. Just take the number in 13 and use it as is. So again, hopefully this video helped you out and hopefully it clarified the deviation stuff. If it didn't, again, please let me know. I'll be glad to go over it with you, whether by email or if you need a Zoom or whatever, that's fine. Again, I apologize for that mistake. Hopefully it won't happen again. And again, have a good day.